Eco.
Là để cho em nghe, chắc là bạn nào em thu được không? Em thu tiếng được không? Nói đi.
So the question here is a rocket is held in play and test fire so that the static CL thrust can be misused. It is found that it does not provide sufficient thrust. Describe how the divergent section of the nozzle could be changed to optimize the rocket to achieve maximum thrust. Uh,
Full screen, bấm full screen dưới đây, bấm vô rồi.
yeah, so we have a rocket uh, at sea level, and the thrust is not enough. We know that the condition for the condition of optimizing DC pressure is equal to pressure ambient pressure, and to control that we change the area section at the exit, uh, and we have three stage. The optimizing stage is the pressure, the ambient pressure is equal to the exit pressure. That's
Yes.
stay here. Yeah, and
Yes.
in this case, it is over expanded nozzle because the ambient pressure is greater than uh, is greater than the pressure inside the nozzle, because the fuel is over expand before it go out of the nozzle. We have the relationship between pressure and the area like this. We uh, when the reaching area cause pressure to be greater, so that we can control it by uh, modify modifying the expanded ratio, A over A star.
Increasing ngay chứ nữa.
Okay.
Dạ giảm nó thì B. Dạ.
Okay, rồi.
At the sea level CL, we can use a stop nozzle. That is a nozzle has a smaller area ratio to to solve this problem. Yeah.
Okay, good.
Okay. Do you have
Good.
any comments on this answer? Is that sufficient?
Uh, yes, for me, it does. It looks very sufficient because you can explain all the under-expanded and over-expanded nozzle. That's good. So, my question to you: do you think that it is appropriate to use a variable expanded nozzles? What do you think? So you have a nozzle like the one in a jet fighter. Okay, name it. For example, Sukhoi. Okay, Sukhoi jet fighter. You can vary the expansion ratio of the nozzle. Do you think it is feasible to use this in rockets? What do you think?
So you mean the solution is a variable? Is it
Yeah,
every
there's a
nozzle?
variable nozzle feasible being used in a convergent divergent nozzle for a rocket? Is it feasible? What do you think? Is it difficult?
That is for also to change its basic ratio in rocket.
Yeah,
Yeah, one
Yeah,
student
you
will
see,
try to answer.
yeah, it's possible because
is it possible? Okay, I'm not sure whether you try to Google this. You try to Google this. How does the variable nozzle looks like in a jet fighter aircraft? For me, in my opinion, I don't think that it is feasible. Why? In convergent divergent nozzles in rockets, you should not have any obstruction inside the nozzle. If you look into the varying nozzles, you have many pin inside. When you have any obstruction inside the convergent and divergent nozzle, what will happen is that you're going to have a hot spot at that particular location, and it will tend to burn the nozzle wall. It cannot convert the heat energy to kinetic energy. It will have a hot spot there. So we are talking about rockets, combustion in rockets. You're talking about very many thousands of degree Celsius in the nozzle itself. So that's why a variable nozzles rarely being used in rockets. It can be used in fighter jet, in a supersonic aircraft, but in rockets they couldn't. It's not feasible yet to be used. When you have this obstruction, it will heat up the nozzle wall and the structure failure will happen. That is my opinion lah. I don't see yet any varying nozzles in rockets yet. That is my take. Okay, do you understand? So that is why during the my first lecture, the scientists are dying to find a rubber-like nozzle. A rubber-like nozzle, but of course, rubber cannot withstand this extreme temperature. So that is why we want to have what you call it, some kind of material that can expand and contract accordingly so that it is matched with the design condition. P exit equal to P ambient. Okay, understand? uh, okay, anyway, nice try, very good, very good. Thank you for the explanation, thank you for your answers. Okay, Dr. Hugh. Next questions. Anybody would like to present?
Okay. Next one, please. Are you ready? So you share your screen. Share your screen. Rồi, ok, cô tắt cái nha. Nghe lại nói nha.
Okay.
Can you hear me?
Yes, I can hear you. You can proceed.
Okay. We are group five, and we are going to explain. For this question, we'll be looking at why most modern rockets use contoured or bell-shaped nozzle instead of conical nozzles. So, first of all, a simple conical nozzle is geometrically simple but forces a performance size trade-off. Its main loss is the divergence loss because exhaust expand radically rather than axially. Using a very small cone half angle, for example, lower than 15 degrees, will reduce this loss, but it will make the nozzle extremely long and heavy, which harming the vehicle mass ratio. Um, the, the bell nozzle will solve this issue. It starts with a steep expansion angle and just after the throat, then gradually curve to redirect the flow so that it leaves nearly axially. This reduces divergence loss much more effectively than a conical nozzle of the same area ratio. For example, an 80% length bell can actually perform slightly better than a conical nozzle while being around like 20% shorter and lighter, which like improve the efficiency of the rockets. Um, so here is the benefits of the bell-shaped nozzle, as I said. So for the comparison of the conical and the bell nozzle here, for the geometry of the conical, it's simple. The divergent loss is high, and length is very long and heavy. So that results in a very lower performance for the same size. While the bell nozzle, even though it's geometrically more complex, the divergent loss is lower and its length and weight is shorter, and so the final performance is way more higher. Um, so for the limitation of the fixed nozzle, and we want to introduce to the adaptive nozzle. Um, there are several adaptive nozzle designed and extendable nozzle that use a fixed and primary section and deploy an extension at high altitude, like the dual bell nozzle use two contours that joins at an interflexion point. This mm, mm, the flow separates for the
Okay. Done? Okay,
uh,
right.
the dual bell nozzle that at low altitude it uses the flow from the upper nozzle area, and at a higher altitude it reattach and use the higher contours. This acts like an extendable nozzle. For the aerospike nozzle, they use a different. They instead of using a closed wall, they use a central spike and let the atmosphere form the outer boundary. This will naturally adapt to the altitude and provide a near optimal performance throughout ascent. That's everything about. So, so in conclusion, the bell nozzle will replace conical due to a shorter and lighter design, reduce divergence loss, improve performance. The adaptive nozzle will increase next evolution for multi-altitude optimization and overall benefit. It will lower the mass, increase the total impulse, and enhance the rocket performance. That's everything I want to say. Thank you for listening.
Okay. Thank you so much. Thank you so much for the presentation and answering the question number six. Why you are using a bell type nozzle instead of conical nozzle? Yes, I do agree with your answers. Bell nozzles can reduce the length as compared to the cone nozzle. Yeah, at least 20% shorter lah if you are uh, if you are doing okay. But my question is, for you, yes, for this chapter nozzles, I did not teach, but I have slide for you. Maybe I can share you in the Google Drive slides on nozzle theory. Okay, you have kind of limitations in designing the angle of the nozzles. Do you know what how much is the maximum half angle of the nozzles that you can take? The divergence for a rocket nozzle with a divergent angle cone. What is the maximum if you tend to have more than this angle, you're going to have a separation. Do you know how much is the angle? No. It's around 30 degree, yeah? 30 degree. So that's why in cone, if you are trying to be giving more higher angle, the gas or the propellant will start to separate from the wall. So this is what we call as an half angle. Okay, half angle. And then I will share you my slide. Dr. Hugh, maybe you can share this to the students. Some of the basics definition, how does this bell nozzle can contribute to the length separation, and then you do have what you call it a swept back angle. You know that in the bell nozzle you have a large increase in the angle after the throat, and then you have a small angle that you diverge back. So this is what we call as swept back angle, or we call it as a turn back angle lah. So you have a difference, theta initial, theta I initial, and theta E. Theta E is the nozzle exit. So the difference between initial angle and the exit angle, this is what we call as turn back angle. Okay, so probably in early in the beginning, you're going to have a 30-degree angle, and then at the exit, you have gradually reduced 11 degree, 8.5 degree. So this is how they play around with the angle for the bell nozzle. And due to this, they have a graph how this turn back angle can contribute to the reducing of the length. Okay, I will share you my slides with Dr. Hugh. I will upload this, and then we share this to the students. Anyhow, good. It's very good try. It's a very good answer. Thank you so much. Okay.
Okay, okay, thank you.
So next question, anybody would like to answer?
Yeah, please wait. One student would like to ask a question.
Okay. Yes.
Hello, I want to ask a question.
Yeah.
in flight performance chapter that I know that those rockets when in orbit they in orbit they want to when they will an object they would make the whole man transfer, but they I know that
You are muted.
sorry
Okay.
okay I continue my question that when they launch a rocket, they always launch the heading. I mean, the heading or the azimuth, the same with the inclination of the object they want to target to. And why I want to ask you a question that why they never do plane chamber and why they cost a lot of fuel rather than they do a whole transfer.
Oh, okay. You were asking about why they use hormone transfer, isn't it?
No, why the flame? Why I said like the maneuvers of an spacecraft when they want to when a line plane that they change the inclination. I know that they when they do the inclination, change the inclination, they cost a lot of fuel for
Yes.
just a few degrees. But when they use the Homan transfer, it costs less fuel. But I don't know why.
Oh, okay. Because it uses a minimum amount of energy, brother. Using a Hoffman transfer, the spacecraft uses a minimum amount of energy. So, looking back at the slide, uh, as compared to the other types of maneuver, the direction, the trajectory, using Hoffman transfer, the aircraft uses the minimum amount of energy to overcome the gravity. So that is why the scientists prefer to use Hoffman transfer because in that particular trajectory, it uses a minimum amount of energy to achieve the target.
Um,
Okay. All right. So yeah, that's why they use a Hoffman transfer. Thank you for asking.
So you can start the lectures for today.
Okay, sure. Let me share you the screen. Okay, thank you, students, for your presentation again. And I'm sorry for the last 2 weeks that I couldn't make it. So now let's focus back to our lecture number 4 on the rockets, on the topic on liquid propellant rockets. So this chapter, in terms of the calculation of mathematics involved, it is where you want to design how much the volume of the tank for the oxidizer or fuel that you need to bring, and the size of it, which is the area of the tank, the volume of the tank, the weight of the tank, as well as the length of the tank. But in order to achieve this, in order to calculate this, the geometry of the tank, what you need to do, of course, you cannot leave chapter number 2 on the nozzle design, where you calculate the coefficient of thrust, where you calculate the what do you call it, AE exit area, you calculate a specific impulse. All those you have to bring along together, so that you need to use this to calculate what will be the the size, the geometry of the tank. So this is the only mathematics that will be involved. Okay. a simple one, but you need to bring all the chapter 2, what you have learned in nozzle theory in this chapter. So, so this chapter will discuss about types of propellant, propellant properties that what we want, okay? What are the properties, desirable characteristics of the propellant that we want, and then type of liquid oxidizers and fuel being used. Next is the propellant tanks. So you have different types of propellant tanks, whether it is spherical, whether it is cylindrical. All right. Propellant feeding system, of course, you have two methods of feeding system, whether the tank itself is being pressurized or call back this schematic diagram in the lecture 1. The next one is a rocket engines for maneuvering, orbit adjustment, and attitude control. Of course, you have a primary propulsion and auxiliary propulsion system. Okay, so usually for primary, it is for boosting, for the ascending, for launching, and then the other types, which is the auxiliary types of propulsions, involve maneuver, adjustment, and also attitude control. And the last but not least, the safety and environmental concerns that we should see in the later part of this chapter. And of course, this chapter, based on our schedule, it will be running for 2 weeks. So I will finish the half of this chapter, and then we will continue back the later part of this chapter next week. Okay, so liquid propellant in a rocket propulsions consists of rocket engines, which we call as the thruster. Yeah? This is where the fuel burn. This is where the injector is. This is where the ignition happen. And then, of course, inside this you have atomization, which what we want both oxidizer fuel to be in gases so that it can mix quickly, and then you have a combustion, and then of course this subsonic combustion happen in a converging section. And of course, before it enters the throat area, the speed, the Mach number of this gas will reach to Mach 1, and then it is then fully accelerated at the divergent section. So a rocket engine is the thruster. It is where you have thrust chambers, and then you have a nozzle, and also the set of tanks for storing and supplying the propellants. So inside the rocket engine, you either have one thrust chamber or maybe many thrust chambers. And then you have a feeding system where you have pipes to supply the propellants from the tank to the thrust chamber. Okay, I think you know this schematic diagram, right? And then a power source to furnish the energy for the feed system. The power for the feed system means that to push the propellants having high pressure entering the thrust chamber. Piping suitable for plumbing and also piping to transfer the liquid under the pressure, a structure to transmit the thrust force, and last but not least, of course, the control devices including valve to start and stop. What do you mean by to start and stop? This is where you do the relight. Okay, so throttling capability, yes, this is where you control the valve. To start the stop, you can see this you use when the rocket started to relight. For example, in the if you can see how does the reusable booster in SpaceX or maybe in Blue Origin's flight, okay, space flight, where the where the fire, the burning, the combustions is stopped, and then it relight back during the descending. Okay, this is where to start and stop. And sometimes also to vary the propellant flow and thus the thrust. Okay, liquid propellants are either expelled from the tank by high pressure gas, or they are delivered by pump to the thrust chamber. Again, I would like to uh, share you again the schematic diagram for the last point there, this is the diagram that we have shared. It is either the tank itself being pressurized, or inside the fuel, inside the pump line, you have a turbo shaft that can pump to give high pressure at the feed line before enter the thrust chamber. Okay, so either one, all right, either one will do. All right, why you need to increase the pressure? It is so that you can have high energy for the combustion. When you have high pressure and then you burn, you're going to have high temperature. You're going to have a huge amount of energy, energy in the form of heat that can be converted into kinetic energy. So this is why we need to have a pump. Similar what happened in an aircraft. Why you need to have a compressor? Because you need to compress the air so that the pressure they increase, you have a lots of amount of energy and can be expand into kinetic energy, right? Okay, some of the applications, rockets, I'm showing you this figure or this table to so that you can see the amount, the value, the range of value for liquid rockets. Okay, because when you do calculation, calculation problems, you can see or you can visualize your answer. Is it appropriate or not? Okay, so in usually in a liquid propulsion, in a liquid and rocket engine, the specific impulse is around 300 to 400, 500, something like that. It's not that much. Solid specific impulse much lesser. Sometimes the rocket also use thrust vector control system. This thrust vector control system, like I've shown you in the first class, where you have gimbal, and this is to adjust the direction of this thrust force. Okay, maybe a random variable thrust feature and engine condition monitoring. Okay, an engine condition monitoring or engine health monitoring subsystem. What is it? Okay, usually, how does the engineers monitor or observe the health of the rocket engine? Is having different pressure transducer or maybe thermocouples at the feed line system. For example, this one location, if you have a pressure drop in these pipelines, so of course you know pressure transducer measure the pressure, then in the system you found out that there is a pressure drop in one of the feed system, you know that there must be a leaking. Okay, so this is how they monitor the health or the subsystem. So measuring device, usually a pressure transducer, usually a thermocouples, or maybe a flow metering control. All right. So luckily, okay, in the Sutton's book, they do have these parameters that can be shared. Of course, if you look at the date for these engines is quite old. So those parameters or those information, it is very, very confidential to share. Apparently, these are some parameters that Saturn can share. SSME RS-25 Rocket 9 engine, look at the thrust, is around 2,183 kilonewton. This is for, I think, for the booster. It's quite high there. And then the chamber pressure is 196. So it is almost 200 times chamber pressure in this engine. And you can see that the mixture ratio from SSME until YF75, the mixture ratio is more than 5. What is a mixture ratio? Mixture ratio is a ratio between m dot oxidizer over m dot fuel. Okay, so the mixture ratio 6.0 means that the oxidizer is 6 times more than the fuel. I have also mentioned this in the previous class that in rockets we do burn fuel at rich condition, means at the stoichiometric ratio more than 1. Okay, so this is stoichiometric ratio, which is different to the mixture ratio. All right, and then you can see that the nozzle area ratio, the epsilon 68, and then if you look into higher expansion ratio, nozzle area ratio, of course, you know, exit divided area throat. Usually at second stage or maybe at the upper stage, the exit area ratio or nozzle area ratio, it is in hundreds. So that is why you can see RL10B2, this is for upper stage. Okay, same as above, upper stage. Yeah. So usually at higher altitude, they have bigger nozzle area ratio. All right. Okay, all right. So this is some of the parameters that you can, what do you call it, visualize the range, the range of the those parameters. All right, and this is another thing. Okay, of course, this is for the Russian rockets. This is the old one. Comparing RD120, RD170, and RD253. So you have different parameter and different geometry. Okay, usually Russian Roscosmos, they like to use RP1, which is the kerosene lah, as compared to American, they preferred methane as their fuel. Okay, all right. So looking at this data, you can see that these are some of the range. Specific impulse is 300. Okay, good. And then you have a mixture ratio, which is oxidizer to fuel ratio 2.6, 2.6. The dry mass is okay. Look at the thrust chamber. Look at the size. Okay, the size, you can see that the diameter of this chamber is around 32 centimeter. Okay, yeah, 32 centimeters. So it's not that big lah. Okay, chamber diameter, and then the chamber length is around 1 meter. Okay, is around 1 meter, the length of the thrust chamber. So you can imagine the size is not that big, but the nozzle is massive. All right, the nozzle is massive. The throat diameter is 183, exit diameter is 1 meter, the area ratio hundreds, and then the length is around 2 meter. Thrust chamber length around 3 meter. Is it a gimbal angle? No, it is fixed. So this one means that there's no thrust vector lah. There's no thrust vectoring. For this one, it is 8, the gimbal angle, 8 degree. And then, okay, so these are some of the parameters for the turbo pump characteristics. You can see that the flow rate is huge. Okay, the flow rate is huge as compared to aircraft. This is 10 times much more than the aero gas turbine engine. Okay. And then the pre-burner characteristic, it is before entering the why why you need to have a pre-burner to heat them up, okay, before it enters the thrust chamber. All right, so there are two categories like what you know before. One is for the boosting, and which is to increase the velocity to a certain altitude, and those for the auxiliary propulsions for the adjustment and attitude control. The thruster includes the combustion device where the liquid propellant are metered. Of course, they need to control, for example, uh, the mixture ratio around 6. So you need to adjust an injected atomized mix and then burn to form the hot gas reaction products. This is then accelerated and injected at high velocity to gain thrust. So in the thrust chamber, of course, you do have what do you call it, injector. it is in spray. Why you need to have an injector? So that the fuel can be optimized. You know that the fuel that you are carrying in, it is in liquid, so before it enters the combustion, not before you, before it start to burn inside inside the combustion chamber, it needs to vaporize, so atomize lah. Okay. Combustion chamber and also the nozzles. So there are two types of feeding system. This is I've mentioned to you before. It is either through gas into the tank, you pump you pressurize inside the tank, or you pressurize at the feed line. So, characteristics of the two category liquid propellant. So you have a boost propulsion, which is the primary one, and then you have the auxiliary propulsions. Okay, so the mission, of course, this boost, you are going to achieve high velocity, but in terms of the duration, is not that high. Okay, it's not that high. So you're going to have maybe around 5 to 40 seconds, maybe in terms of minutes, but you are dealing with total high impulse. Okay, and then high thrust. Sometimes you use a cryogenic fuel. I will explain to you what do you mean by cryogenic, and also a storable fuel liquids. Auxiliary propulsion, okay, it is usually at the side of the rocket body, and this is for altitude control. The thrust is not that high. It's around 0.001 newton up to 4,500 newton, and it is radiation cooled. And then you are sometimes it use monopropellant. Monopropellant is some kind of stored coal gas, one single propellant. And it can duration for the firing, it can up to the several hours. Okay, so type of propellants. Okay, the common desired characteristic of the propellants that we want. Okay, there are, and there are listed 10 of them. I will explain to you later. So propellants are the working substances in the rocket engine. It is a gas. Okay, constitute of undergoing chemical and thermodynamic changes. Thermodynamic changes, why? Because it converts lah. It converts from chemical energy to heat energy. The term liquid propellant embrace in all various propellants stored, and maybe one of the following: either it is oxidizer, oxygen, nitric acid, nitrogen dioxide, or fuel, kerosene or RP, alcohol, liquid hydrogens, chemical compounds, or mixture of oxidizer and fluid capable of self-decomposition like hydrazine, and any of above, but with a gelling agent. This is also some of the possible propellant being used in terms of gel. Okay, so actually, what are the characteristics that we want or to suit as a rocket propellant? Number one, the propellant, of course, what you want that it must have high chemical energy release. So the heating value should be high so that it can have higher combustion temperature. So it will can lead to high characteristic velocity, C star. Okay. And then secondly, you must, of course, you want to have a low molecular weight of the combustion product. Okay, means when you combust, you have reactant and product in chemistry. Yeah? You have a reactant and product. The product must have a low molecular weight product. Why? Because it can lead to high exhaust velocity, V exit lah, and thus you're going to have high specific impulse. This is the second one. The third one, the characteristic that we want to be a good propellant is that it should have a high density. Why? Because that when you have a high density, you're going to have a large amount of chemical energy that can be stored in the smallest volume so that your tank can be in a smaller size and can be in compact design. Okay, so high density. Yeah. Number four, of course, what you want from the propellant is that it is easy to ignite, even under the low pressure condition. Fourth one. Fifth one, you want it to be physically and chemically stable with respect to time. Means that uh, of when the rockets ascending, okay, you're going to have different pressure, and then of course it will involve different temperature. Temperature gradient will be high, pressure gradient will be high as well, but it doesn't alter the composition or the chemical of the propellant itself. That's why we call this as stable. Number six is, of course, we want to have try to have a smoke-free and non-toxic in nature. Seven, easy to manufacture and also to handle, so that it can be much cheaper. Easily available and low price, less prone to explosion hazard, and the last one is low emission level. Okay, so in the slide you will see that there are different types of oxidizer and fuel listed out later, inshallah. All right, so these are some of the type of propellant. Number one, we call this as a bipropellant, which is consists of two separate liquid propellant, oxidizer and fuel. Of course, they are being stored separately, then mixed inside. Next, you have a hypergolic propellant. What is a hypergolic? Hypergolic is a propellant where it can self-ignite when it is in contact. Okay, so you don't need any ignition or igniter. But the non-hypergolic bipropellants, you need something in the source of heat, or maybe spark plug, or maybe electric discharge, so that you can ignite this. Okay, so hypergolic, you don't need igniter. When the both propellants combined contact, it will self-ignite. This is hypergolic. Third one is a monopropellant. Of course, these two, the name implies mono means one type of propellant. It contains of oxidizing agent and combustion method in a single liquid substance. It may be stored in a mixture where several compounds, or it may be in the homogeneous material such as hydrogen peroxide and hydrazine. Monopropellant usually are stable at ambient storage condition. However, it can decompose and yield hot combustion gas when heated. Okay, so in the ambient condition, it is stable, but when you have heat, okay, it can start to decompose. Cold gas propellants such as helium, argon, and nitrogen. This is can be stored in ambient temperature, but of course at high pressure. Why you need to have high pressure? You need to have high pressure so that you can have a huge amount of energy, and as well that you can reduce the volume of this tank. So it give, of course, low performance because there's no combustion happen. It is just expelling this cold gas outside. Usually cold gas propellant, it is being used for auxiliary propulsion system. Okay, it give about low performance but allows a simple system and usually very reliable. They have been used for roll control and attitude control. So like I said, this is for auxiliary propulsion. Next, cryogenic propellant, of course. Okay, this cryogenic, for example, you're talking about liquid oxygen, you're talking about liquid hydrogen. So the gas, oxygen, it is in gas. But how you want to make it in liquid? You liquefy it, you give a low temperature and high pressure. Okay, so this is how they make the oxygen to be liquid and hydrogen to be liquid. So a liquid gas at lower than ambient temperature, such as liquid oxygen, so you have to store them at negative 180 degrees Celsius. while high liquid hydrogen negative 253 degrees Celsius. So this is to vent the storage tank and minimize the vaporization losses unnecessary with this type. Cryogenic is good. Why I am saying is good, because if you are burn hydrogen, you're going to have a huge amount of heating value, huge amount of energy, heat energy that can be converted into kinetic energy. But you need to have an extra system so that you can store this in liquid. Okay, so that is why when you look at the during the launching, you can see many gas evaporate outside the what do you call it, the rockets. So this is because of this liquid hydrogen. It's very cold. Storable propellant such as nitric acid and gasoline, these are liquid at ambient temperature and of course at a modest temperature pressure, sorry, and it can be stored for a long period. Space storable propellant, this is remain liquid in space environment. Some they are using water as well. Gel propellant, it is a thiotropic liquid with a gelling additive. Of course, this is behave like a jelly or thick paint, but it can flow under pressure. This is still in the experimental stage yet. Hybrid propellant, okay, this is uh, my area where you have both oxidizer and fuel at different physical states. So for example, oxidizer is in liquid or gas, the fuel in solid. Okay, so this is the only mathematical formulation for this chapter. So using this equation, you can actually design the volume size of the tank. Okay, R is the ratio of m dot oxidizer over m dot fuel. So m dot, which is the total mass flow rate, is equal to the summation of m dot oxidizer plus m dot fuel. And if you know the R, which is the mixing ratio, so you can calculate the m dot oxidizer, or you can calculate m dot fuel. So the above four equations are often valid when W dot, which is weight flow rate, are substitute for m and m dot. You will see this in this slide. Okay, there is one example in the Sutton book, example 6.1. Let's go to this example and discuss. A liquid oxidizer, liquid oxygen, liquid hydrogen rocket. So you have liquid oxygen as oxidizer, liquid hydrogen as a fuel, rocket thrust chamber that produce 10,000 pound thrust. Okay, so you know the thrust is 10,000. Okay, and that operates at the chamber pressure 1,000 psia. So this is P1. The mixture ratio of 3.4. What is 3.4? This is the R. Okay, so this is the R, 3.4. Has exhaust product and the mean molecular mass M of 8.9 pound per pound mole. Combustion temperature T1 4,380 degree Fahrenheit, and the specific ratio of 1.26. What is a specific heat ratio? It is K lah. K. So K is equal to Cp over Cv. So 1.26. Now determine the nozzle throat area. So the question is to calculate AT, nozzle throat area, AT, nozzle exit area, which is A2, for the optimum operation where the P3 equal to P2 equal to 1.58 psia. The propellant sea level weight, so you have one nozzle throat area, and then second one nozzle exit, and then the third one weight, propellant sea level weight, and the volume flow rate, and the mass propellant requirement, which is M lah. Okay. total propellant requirement, which is weight lah, for 2.5 minutes. So you need to change this into second of operation. Let's assume for this problem, the actual specific impulse are as 97% of the theoretical, and the thrust coefficient is 98% of the ideal value. Okay, so this is the question: to design the to know what is the weight of the propellants that you need to bring, and then the volume of the propellant that you need to bring. Okay, so going back to chapter 2, which is the nozzle theory. Number one, of course, you need to find the V2, the exit V2, the exit velocity. Why you need to find the exit velocity? Because you need to because you need to use this to find other parameters such as the CF, such as the AT, and then what else? Mm, M dot, yeah, M dot as well. Okay, M dot, where is V dot as well lah. Okay, so according to this equation, okay, C is equal to V2. So take this V2 is equal to this. Okay, bear in mind, brothers and sisters, this equation, it is for SI condition, but since this is in British unit, so you need to use this multiplied by G, gravity. So that's why this is the equation. 2G KR. So you know G is a gravity, K is the specific heat ratio, R is the universal gas constant, T1 is given chamber temperature, molecular weight given 8.9, and then you have P2 over P1. What is P2? P2 is 1.58. What is P1? P1 is the chamber pressure, 1000 psi. Okay, so you substitute this and then you get straight away the exit velocity. Okay, so from the exit velocity, so the optimum expansion, okay, optimum expansion is 431. What is this? Okay, specific impulse ISP is equal to C over G. Okay, this is in chapter 1 definition. Okay, ISG is equal to C over G, but for optimum, the C is equal to V2. Okay, so V2 over G. So V2 over G, V2 is there, 13,000. G is 9.81. So you have an ISP of 431 second. So this is a theoretical, but in reality, the actual specific impulse is 97%. So 97% multiplied by 431. So that's why you got 418 second. This is the real one. So you're going to take this, yeah? And then that is done for the ISP. The theoretical ideal thrust coefficient. Now let's find the CF. Why you want to find the CF? Because from the CF, where's the cursor? Okay, from the CF, using this equation, so CF is equal to blah, 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 or equal to this value. Okay, when you calculate, because this term, you can calculate directly, and then you can substitute here in the first equation to calculate what is AT, the area of the throat. Okay, so that is why you need to use this equation. This is why you need to calculate the CF. Okay, so next is to calculate the CF using this equation. So CF is around 1.76. So 1.76, of course, this is a theory one. Stated here, it is only 98% of the ideal value. So 1.76 multiplied by 98% is equal to 1.72. So 1.72 substitute here in this first equation. So CF is known, force, which is the thrust, is known, P1 is given, so you can calculate for AT. So AT, the throat area is around 5.8 inch square. Okay. All right, done for the AT. Okay, done for the CF, done for the AT. Next, the optimum area ratio, okay, can be found. Okay, how to calculate this one? Okay, since you know that you since you know that it is at the P2 is equal to P1, okay, sorry, P2 is equal to P3. So you know that to calculate expansion ratio, so you can use this equation. Okay, so you can use this equation. So this is K is given, Py, okay, Py it is P2 lah, okay, Py is P2, Ay is A2, so At is known, Ay is known. So you can use this equation so that you can calculate the so you can calculate the expansion ratio to be 42. Okay, use this equation to calculate 42, the expansion ratio. So since 42 is known, 42, area throat is known, so you can calculate A2. So 42 multiply what is the throat area, 5.8 inch. So the A exit A2 is 244 inches square. So you can use this equation, or you can also use the diagram or table lah. Okay, so next, using the propellant weight flow rates. Okay, so since F is known, thrust is known, ISP, specific impulse, is known, so you have the total weight flow rate is 24 pound per second, and then giving R 3.4, so the weight, the oxidizer weight flow rate is this equation using the previous equation that we have. Okay, so substitute, you have 18.5, and then similar for W fuel, what W dot fuel is 5.45. All right, okay, so that is the weight flow rate. Now you want to find the volume flow rate, so you just divide by density. Density of our oxidizer and density of the fuel. Uh, so you have volume flow rate of 0.261 and 1.24. Okay, now done. But you want to know that how much you should bring. You already know the weight flow rate, the volume flow rate, but you don't know how much volume or how much weight that you have to carry. So using the 2.5 minutes of operation. So since this is volume flow rate and weight flow rate, so you simply multiply by 152. So you're going to have for the weight of the oxidizer 18.55, which is this one, 18.55 multiplied by 152 minutes or 152 second. So you actually require 2,820 pound of oxygen, 828 pound of hydrogen, volume 39.7 feet cube of oxygen, and 188.5 feet cube of hydrogen. So this is the weight and the volume. So my question for you, how you want to calculate the length? You know the volume, so how you want to calculate the length of the tank? It's easy. Let's assume that the exit, not assume, let's assume that the biggest area for the rocket is nozzle exit. So nozzle exit, what you have is around 244. Okay, exit area 244. So you know the area, you know the volume, so you can calculate what will be the length of the tank. Okay, so this is how. All right, because area multiplied by the length is volume. Okay, okay, all right. So you can try to practice this. I leave this to the I leave this slide to you so that you know which equation that you must use. Looking at this equation, I know it is familiar. I know I have given you the Excel sheet, but I wanted you to know how to use it and when to use it lah. Okay, so for this one, this is to calculate the pressure, ambient pressure, stagnation pressure. This is the isentropic relation. This is to calculate the C, which is or the exit velocity. mass flow rates. This is the expansion ratio at any location. So AT over AY it is after T. Okay, so you have throat area, throat. Y is any area. So for example, you want to calculate at the exit. So this is A2 lah. AY replaced by A2. But of course, if you want to calculate A2 here, you must know what is the P2 to substitute in PY and PY here. Okay. And then this is the CF to calculate the A throat. All right. Next is the liquid propellants. So these are the only mathematical equation. Of course, we do have many equation, but I don't think it is suitable for undergraduate yet. For example, you do have to calculate the combustion instability where you have the oscillation, and then you do have the ignition automation equation, but I don't think that is meant for undergraduate level. If you want to know this, you can read the Mishra book in I think chapter 6, I think, okay, where they give you the overview, the calculation for not chapter 2, chapter 8, sorry. So chapter 8 in a liquid propellants. So there you have kind of calculating the the instability, the ignition, the fluctuation, and then the atomization and etc. So I won't go into that extent. It is just fair enough on how to calculate, on how to design the tank of a liquid rockets. Right. So at the present time, we only use three liquid by propellant combination. Okay, you have different types of propellant kan. So you have cryogenic oxygen hydrogen propellant system, or liquid hydrogen hydrocarbon propellant. Hydrocarbon propellant is kerosene lah, RP. Okay, usually the first one, cryogenic, you need to have a proper system, of course, because you are dealing with cryogenic fuels. It has a tremendous amount of energy that you can have, but in terms of complexity, storing and etc., you need to have additional system. Okay. Liquid oxygen and hydrocarbon, it is meant for booster stage, same. Okay. Having a higher average density, more compact booster, and with less inert mass compared to the cryogenic one. Not a single bipropellant combination, but several ambient temperature storable propellant combinations used for large rockets in the first and second stages. Okay, all right. So these are some of the liquid propellants that we have and the physical properties of it. Liquid oxygen, nitrous oxide, nitrogen tetroxide, nitric acid, RP, liquid hydrogen, liquid methane, monomethyl hydrazine, UDH, and also water. Looking at this, you can there are some of parameters, okay, properties that we want. For example, the what do you call it, in in terms of giving more energy, you can see that liquid hydrogen 446, methane 510, hydrazine much higher, and water also much higher. But why don't you bring water? Okay, water, it is it's good actually, but in terms of the combustion, okay, it's difficult to sustain. All right. And then how do you make your fuel, your tank small? So look at the specific gravity. If you have lesser specific gravity, okay, less specific gravity means that your tank can be much smaller. Okay. All right, this is some of the properties, this one in terms of stability lah. So let's say a liquid hydrogen, okay, if you have different range of temperature, so the specific gravity started to reduce. Okay, liquid hydrogen in this part, okay, methane, and etc. This is to show how does the property varies at different conditions such as temperature, such as vapor pressure. So propellant properties, of course, we want to see uh, in terms of economic factor is that it must have low cost. But again, low cost propellant doesn't give you better heating value. Okay, usually expensive propellant, uh, uh, not expensive, it means complex propellant to handle, for example cryogenic fuel. It give you better heating value. Toxic propellants, of course, it is expensive because it give you better heating value, but it is toxic and it is difficult to handle. Uh, so you need to have additional step of precautions during the operation. Okay, so this is the thing that we need to watch out in terms of economic factor. But let's compare this this parameter with the aerogas engine. Okay, in the aerogas engine, usually in the turbine in the temperature, okay, it goes up to 1800 until 2300. But in rocket engine, you are dealing more than 3400 kelvins, quite high. And in aircraft, you are dealing with 5 to 40 atm pressure in the combustion chamber. But in rockets, up to 200 atm high pressure in the chamber. In terms of flow rates, okay, as you compare with aircraft, flow rates is this one. Okay, flow rate in aircraft engine is around what, 2.5 kilogram per second, but in liquid rockets you are dealing with much higher flow rates, around 600 kilogram per second. So this is why rockets engine is not fuel efficient as compared to aerogas turbine. So that's why it is expensive. All right. So next, I think this is going to be my last slide so that we can continue in next week. So performance of propellants, we want the rocket engine to be compared on the basis of these are the parameters that we want. Specific impulse ISP, the higher the better. Exhaust velocity, the higher the better. Characteristic velocity, the higher the better, and other engine parameters. The specific impulse and also the VE, you can see that it is a function of pressure ratio, K, specific ratio, temperature T1, mixture ratio R, and molecular mass. So looking at the equation, specific impulse and exhaust velocity, look at this equation. This equation, you can see that exit velocity depends on K, depends on T, depends on molecular weights, pressure. Okay, so that is the idea. If you can have a better P2 over P1 ratio, you can increase the V2. If you want to have T, chamber temperature higher, you can have a better V2. If you do have K value less, you can also have a better V2. Less, sorry, not less. Okay, you have a different K, different K. So this K varies from 1.2 until 1.6. Better M lah, M, molecular weights. Okay, like mentioned before, you want the product to have small molecular mass, for example, in hydrogen, so you can have a better V2. Next, for high performance, you must have high. So this is for the mixture desired and can yield high chamber temperature, high heating value, and energy that can be converted into kinetic energy. Low molecular mass M for the combustion product is also desirable. This can be accomplished by fuel rich in hydrogen octane when significant portion of hydrogen can be injected or produced remains uncombined. The last one but not least is the best mixture for many byproduct is not stoichiometric, like I said. In rockets, you don't burn at stoichiometric condition. I know that in a stoichiometric condition, you're going to have complete oxidation and also high flame temperature, but you want to have a huge amount of low molecular mass reaction product. This happen in a fuel rich condition. Okay, all right. So I think Dr. Hugh, students, I have to stop here. I hope that you any questions from the students that you would like to ask. It's already halfway.
Thank you for the lecture. So please let me ask the student. Is there
Uh,
any questions about
any questions?
any questions about today lectures?
Any questions about the lecture? Any?
Yes, today lectures or anything.
Have you tried to use the Excel sheet, students?
Yeah.
Have you tried using the Excel sheet that I have shared? Not yet.
It's on our Google Drive.
Dr. Hugh didn't share.
It's already there.
ah, it's kind of easy to use, but of course, better you start with on how to use it because you need to practice as well. Let me share you this. Have you shared the Excel sheet with the student, Dr. Hugh? Not yet. This one. Have you shared with the student? Oops, sorry. What is the Excel sheet? This one. Have you shared this with the student? Not yet.
Yeah, already.
Okay.
Already shared on the drive.
I
Okay.
see.
Okay.
I see. So the left side is the input parameter, and the right side is the output, and the right side is the output. The left side all the input that you can insert, and then the right side. Okay, you can try. You can try to have a go. Uh, because I know that you have many equations, and I I suggest you not to memorize the equation, just know on how to use it and when to use it. That's it.
Yeah.
Okay.
Yeah.
All right.
Okay.
So you don't have any questions? Can we end our class?
Yeah, sure. Yeah, sure. Thank you very much. They will have some time to explore the files
All right.
and us next week. Okay.
Okay.
So take good care of you. Thank you
Okay.
very much,
You're
and see
welcome,
you
Dr.
next
Yu.
week.
Okay. See
Yeah.
you next week.
See you next
Bye.
Bye. Thank you.